Machine learning is a subfield of artificial intelligence that focuses on developing algorithms and models that enable computers to learn from data and improve their performance on a specific task, without being explicitly programmed for that task. The ultimate goal of machine learning is to allow computers to make accurate predictions, identify patterns, or make decisions based on the patterns and relationships found in the data. The general process of machine learning involves the following steps. Data collection. Data collection involves acquiring relevant data from various sources, such as databases, APIs, web scraping, sensors, or user input. The data should be representative of the problem domain and cover a wide range of scenarios to improve the model's generalization. The data can be structured in tables or databases, semi-structured, example, JSON, or unstructured, example, text, images, audio. Data preprocessing. Data preprocessing is a crucial step to ensure the data is clean, consistent, and ready for training. It involves several tasks. Handling missing values. Missing data can be imputed using various techniques, such as mean, median, mode imputation, or more advanced methods like regression imputation or matrix factorization. Outlier detection and treatment. Outliers are data points significantly different from the majority of the data. They can be removed, transformed, or replaced with more appropriate values to avoid negatively impacting the model's performance. Feature scaling. Features often have different scales, which can lead to bias in some algorithms. Common scaling methods include min-max scaling, scaling features to a specific range, and standardization, scaling to have zero mean and unit variance. Encoding categorical variables. Categorical variables are transformed into numerical representations so that algorithms can process them. This can involve one-hot encoding, label encoding, or more advanced methods like target encoding. Data splitting. The dataset is split into two or more sets, a training set used for model training, a validation set used for hyperparameter tuning, and a testing set to evaluate the final model's performance. Feature engineering. Feature engineering is an art that involves creating new features or transforming existing ones to improve the model's ability to capture patterns and make accurate predictions. Domain knowledge is often crucial in this step. Feature engineering techniques include polynomial features, creating new features by combining existing ones through addition, multiplication, or exponentiation can enhance the model's ability to capture complex relationships. Dimensionality reduction. Techniques like principal component analysis, PCA, or T-distributed stochastic neighbor embedding, TSNE, can reduce the number of features while preserving essential information. Feature selection. Selecting the most relevant features can reduce model complexity and prevent overfitting. This can be achieved using statistical tests, feature importance scores from models, or recursive feature elimination. Time series transformations. For time series data, lag features, moving averages, or other time-based transformations can reveal important temporal patterns. Model selection. Choosing the right model is essential for achieving the best performance. Different machine learning algorithms have strengths and weaknesses depending on the problem and data type. Decision trees, useful for both classification and regression tasks. They partition the data based on feature values to make decisions. Support vector machines, SVM effective for classification tasks. SVMs aim to find the optimal hyperplane that best separates different classes. K-nearest neighbors. KNN, a simple algorithm that classifies data based on the class of its k-nearest neighbors in the feature space. Neural networks. Deep learning models with multiple layers of interconnected neurons can handle complex patterns and hierarchical representations. Random forests. ensembles of decision trees that provide robust predictions by averaging multiple tree outputs. Gradient boosting machines, GBM, an ensemble technique that combines weak learners, typically decision trees, to create a strong predictive model. Clustering algorithms, K-means, DBSCAN, and hierarchical clustering are used for unsupervised learning tasks, where the goal is to group data points into clusters based on similarity. Reinforcement learning algorithms, Q-learning, deep Q networks, DQNs, and proximal policy optimization, PPO, are commonly used for training agents in interactive environments. Model training. During training, the chosen model is fed with the pre-processed training data, and the model's parameters are adjusted iteratively to minimize a loss function. The loss function quantifies the error between the model's predictions and the actual labels, for supervised learning, or measures the model's ability to find patterns, for unsupervised learning. The optimization process aims to find the model parameters that minimize the loss function using algorithms like gradient descent or stochastic gradient descent. Model evaluation. To assess the model's performance, it is evaluated on a separate testing set that the model has never seen before. Common evaluation metrics depend on the task. Classification, accuracy, precision, recall, F1, score, area under the receiver operating characteristic, ROC, curve, AUC-ROC, and confusion matrices. Regression, mean absolute error, MAE, mean squared error, MSE, root mean squared error, RMSE, R-squared, etc. Clustering, silhouette score, Davies-Baldwin index, etc. Reinforcement learning, cumulative reward, success rate, or performance metrics specific to the environment. Hyperparameter tuning. Most machine learning models have hyperparameters, which are set before training and control the model's behavior. Tuning these hyperparameters is essential for obtaining optimal model performance. Techniques like grid search, random search, and Bayesian optimization are used to find the best hyperparameter values based on cross-validation performance. Model deployment. After selecting the best performing model and hyperparameters, it is deployed in real-world applications to make predictions or decisions on new, unseen data. Deployment may involve integrating the model into a web service, mobile application, or any other platform. Monitoring and maintenance. Once deployed, machine learning models may require continuous monitoring to ensure they perform well and provide accurate results. Monitoring may involve tracking model drift, changes in the data distribution over time, retraining the model with updated data, and maintaining the infrastructure for efficient prediction delivery. Machine learning is an iterative process, and the models may go through multiple cycles of improvement and refinement to achieve the desired level of performance. Domain expertise and a thorough understanding of the data are crucial for the success of machine learning projects. Additionally, ethical considerations, fairness, and transparency in model decision-making are increasingly important aspects in the development and deployment of machine learning systems.